So in fact, whenever you have definitions, it's a good idea to think about them so much that you come up with other ways of stating them. So I'm going to state for you an alternative way of saying what it means for a set to be open, and in fact, this alternative way uses something we just learned. It uses our notion of an open interval. Which reminds me, did I mention that these are unbounded open intervals? I think I forgot to say. So these are unbounded open intervals. And in fact, the one we were just discussing, AB, like this, where you include A but not B. In fact, you can do the same thing like this. You can have A, B like that. Think about what that means. So just to have terminology, so I don't have to use so many words every time. These are, we can call these half-open intervals. So this half-open intervals. So they're kind of like an open interval on one end, but on the other end, they're not. So we call them half-open intervals. They're also bounded. Bounded intervals, they're called half-open intervals. Okay, our definition of open set in R can be rephrased as follows. In fact, this is kind of this is really a cleaner way of saying the definition. In fact, so a subset U in R is open if, so it begins the same, if for every point P in U there exists, but instead of saying there exists a number epsilon, you can actually just say that there exists something else we were just investigating, which is an open interval. In fact, it could be bounded or unbounded. There exists an open. I'll give you that one in a second. In fact, if you want to see how you arrive at that, here's an intermediate step. You can still say there exists an epsilon greater than 0 such that, but instead of talking about absolute value and distance, you can just refer to the specific open interval, which is P minus epsilon to P plus epsilon, which has been appearing in our pictures, such that this interval here, now this uses the idea of subset, is a subset of the set U. So that means, so not difficult to see why that's saying the same thing. An element in here, now that we know what this means that number is between these two numbers, which means the distance is from P is less than epsilon, so it's an element of U. So it's just a rephrasing of the definition. In fact, you can clean it up even more and say that for all P and U, there exists, and now you can, if you want, dispense entirely with the idea of this number epsilon and only talk about some open interval that's a subset of U. So there exists an open interval. Let's call it I, just give it a name. Such that, well, first of all, P has to be an element of I. Notice P is certainly an element of this interval here. Such that P is an I, I is a subset. So this is a very clean way of stating what an open subset of R is, once you already know what we mean by an open interval. So an open interval is an example of an open set, but this gives you all the other examples of open sets. So the picture is even simpler now. It's just that, so if I give you a subset of R that's open, and you take any point in that subset, you have to be able to find an open interval, and it doesn't have to be centered at P. It can be any open interval. But it has to be a subset of U. Okay, so let me remind you about something that you've probably seen before. You've certainly thought about it before. The idea of a union of sets. This is an important to have an understanding of this in topology. So in fact, X and Y are any sets. When we write this, X with a U in between, a big U, it means stands for union. So X union Y is the set of all things. The set of all things X, such that, well, X is in X or X is in Y. Now it could be in both. If it's in, it could be in both, and then both of these statements are true. Okay, that's the union of sets. Very simple. So we can define unions like this as well. In fact, here is the standard notation for this. So this is just notation, okay? And what this notation means is the set x1 union the set x2, but then you continue the process. x3, and the only way to write it really is to put dot dot dot, because we're just, so the number of sets is just n, so we union until the set xn. Now there's something to think about, the fact that it's the order in which you apply this operation. If you take the union of these two first and then this, or these two first and then this, it doesn't matter. But in fact, what you arrive at is simply what? The set of all things x, such that x is an element of the set, so the big X. And the key logical word here is for some, just like in the example with going outside when it rains. It's not for all days, it's for some days. So this is for some I, in fact, some I from 1 up to n. But this is just defining the union of finitely many sets. The sets could contain whatever. They could contain numbers, but they don't even have to. This makes sense much more generally. Okay, and you can take this idea even further. Sets are kind of strange things in mathematics, but it's necessary sometimes to consider a set of sets. Well, here's a set of sets. Here's a set of n sets that I took the union of. So the way you would write this out is this. I have x, and here I'm just writing the symbol alpha. You can use whatever symbol you want. alpha is an element of A. So I have a set A, and then for each element of A, I have a set called X with that symbol down there. So this is a set of sets, but it sounds better if you say collection of sets. Collection of sets. I'm sure you can think of it. You have to be a little careful, but you can think of it as a set of sets if you want. So we write this. We say U for union, and down here we write alpha, an element of A, and we write the X alpha. So this is just notation to mean that you're taking the union of all the sets X alpha. And now the thing is that unlike in this example where you're taking the union of finitely many sets, this could actually mean the union of infinitely many sets, which is no problem whatsoever. You can write out what it means exactly like this. It's the set of all things X such that that thing is an element of the set X alpha, and once again, for some alpha in A. So this is the idea of taking the union of an arbitrary collection of sets. And this is important to think about in topology. In fact, I'll show you why it's important for us right now by giving you the following problem, which is, it's one of these problems that, well, a lot of problems in mathematics are like this. They sound complicated, but they're really simple. So this is a problem that's deceptively simple. And the problem is this. You have a collection of sets where each set U alpha is a subset of R and it's open, this definition that we've been discussing. Well, you can take the union of all of those open sets, and it turns out, and again this is deceptively simple, it's really easy to see, really easy to see, that this is again an open set. So really simple, yet really important. So, there's even not very much to write out in terms of proving it, so the problem is really just to think about this while you're walking around and see, oh yeah, of course. Okay, along with union, we have the idea of intersection. In fact, I won't even write out all the definitions, I'll just tell you what you have to change. So notationally, we replace the big U with the big upside down U. Whenever you saw the word or in the definition of union, you replace it with the other logical word, and. So the intersection of two sets is the set of all things that belong to both sets, to this and that, to both sets. And then, at some point you have to, in those definitions, you have to replace the word some with the word all. So if I take the intersection of an arbitrary family of sets, it's the set of all things such that X is in that set for all sets in in the collection of sets. That's the intersection of the family of sets. So they're very simple things to define, but really important to understand. So now the question should be, since you just were thinking about the deceptively simple problem, so is it also a deceptively simple problem that the intersection of closed sets has to be closed? So what do you think? If I have this is an open set. For all alpha in A. So this is a question. Does this imply that the intersection of all of those, let's call it U, I guess. So apply to this. So, well, I didn't call it a deceptively simple problem, so that means it's either true but not so simple, or it's false. Which one do you think? Well, let's investigate. So for example, e.g., what happens if I take the intersection of two bounded open intervals? Can we at least figure out what's going on there? Well, so let's draw a picture. Let's draw a picture like this, where we put A here, B here, C here, and D here. So I guess I'm discussing the special case when A is less than B, less than C, less than D. So what do you get when you take the intersection in this case? What's the intersection? So intersection means all of the things, in this case all the real numbers that belong to this and to this. So what do you get? You get nothing. More precisely, we say that you get what's called the empty set. It's the set that contains nothing, has no elements whatsoever. So actually, so there's a question we could have asked right after our definition of open set. Is the empty set open? You have to think very carefully about the logic. Open means that for any point you can find an epsilon, etc. And remember our example of a set that was not open. Remember what that meant? That you could find a point with the following property. Oh, but can you find a point in the empty set? If you even stop there, if I say there exists a point in here such that, I'm already telling a lie, right? Because it contains nothing. So the empty set is open. Yes, technically. It's one of those things I think where they call vacuously true. It's true simply because the thing contains nothing. Yes, technically. Okay, so this intersection of two open sets is open. Okay, what about if we did it like this? What if we put, in fact, if I make B equal to C, so now it looks like this. B is the same thing as C. Does anything change? Does anything else change? No, in fact, I think even if B and C are equal, still there's nothing in both these intervals. So it's the same actually. So in fact, if A is less than or equal, so in fact what's true is that if B is less than or equal to C, you get the empty set, it's open. Okay, so the more interesting thing could be something this, if we have A, and now let's actually put C next, and now put B, and then put D. So in this picture I have A less than C, less than B, less than D, but I'm still thinking about the same intersection of sets. So now what is the intersection? So I need all things that are in between A and B, and are also in between C and D. So it looks like in this case I'm going to get something. We get, well, we get the open interval from C to B. So is that open? Yeah, it is. So in this case, once again, it's open. So you can go through the other cases if you want. I mean, you can switch around the orders of A, B, C, and D a little bit more. The conclusion is pretty clear. Checking case by case. In fact, not only do you find that intersection is always an open set, we see that AB intersect CD is another open bounded interval. Useful fact to know. So in fact, let's well, it's a proposition. Let's actually do a little proof here. Why not? So suppose U and V are open subsets in R. Then, in fact, I think we can come up with a complete proof of the fact that U intersect V is open as well. Maybe we'll do the proof after a 5-minute break.
Yes.
Okay?
We're doing the
5-minute break.
after.
Yeah, we'll do the proof after the 5 minutes.
Okay.
Do you remember? No.
Mm-hmm.